All right. Good afternoon, everybody. It's a pleasure to be here. My name is Kevin Mackie. I'm a professor and also associate chair of civil, environmental, and construction engineering. So just very briefly about me, my research areas overall relate to performance-based engineering, so qualifying the performance of infrastructure and using high-performance materials and composites for repair and retrofit. Another major area that I specialize in would be the use of engineering uncertainty, so quantifying error propagation and probabilistic methods, and then structural dynamics and nonlinear modeling, primarily as they relate to bridges, but also other structures. On the teaching side, taught all the way from large section statics through probabilistic and nonlinear modeling courses at the graduate level. And then just a couple of things I wanted to mention for recent achievements is I was the leader of the department effort for the most recent ABET reaccreditation. So obviously I'm pleased about that. And then just wanted to mention to everybody that I'm the ASCE, American Society of Civil Engineers, the UCF chapter advisor, and they just recently won, or they received an honorable mention, which is one of the top accolades for student chapters in the United States. Also, just to mention, I do a significant amount of advising, so I'm also somehow involved in the undergraduate enterprise here in the department. So the motivation or the background to a lot of the research questions that I tackle are quite easily articulated because you can see them around you. And obviously the National Academy of Engineering has included it as one of their grand challenges, and that's to restore and improve the nation's infrastructure. And the American Society of Civil Engineers always does a good job of bringing this to the attention of the public through their report cards that get issued. And the 2021 report card just recently came out, and we actually improved to a C- grade overall, but obviously not only the status of the current infrastructure, but the needs and the investments in order to improve or to mediate some of the issues is a staggering number. And more than likely, a lot of you are familiar with some of the discussion currently in the political realm as to what the infrastructure improvement bill would contain. So what are the research challenges associated with that? So part of it is obviously for new design and repair and retrofit. And a lot of this relates to the application of new materials for infrastructure. So what can we do at the experimental, analytical, and numerical level to understand the behavior of these? And then for the existing infrastructure, it's important to monitor and evaluate condition. So that's a lot of times using technology and modeling to make decisions, obviously, about maintenance and improvement. And then finally, looking at it at a more system level, asset management, or making decisions across multiple infrastructure systems with the eye to improving the lifespan. And obviously, this is very pertinent in the current environment where urbanization is becoming obviously more prevalent, and extreme events and climate change are more frequent than ever. So very pertinent needs. So some showcases of existing or recently completed projects. One of them is fiber reinforced polymers for repair. For those of you who are not familiar, it's a fiber material that's woven and impregnated with a resin and adhesively bonded here to the outside of reinforced concrete infrastructure, which dramatically improves the stiffness and the strength. My particular research interest in this is it's an existing system. I have nothing to do with it, but polyurethane is a material which you're probably all familiar with in plastic goods that you use, but it to date has really not been used for structural adhesive. And the interesting part about that is that it's actually a very weak and flexible material, as opposed to what you might expect from something for strengthening. But actually through these kind of interesting interfacial nonlinear behaviors that happen between existing and the repair, we're actually able to mobilize a strength that's sometimes higher than existing products that are epoxy-based out there. So a lot of this was experimental work that was done in our lab. You can see some examples here for a wide variety of different scales. And then the associated finite element or numerical modeling that accompanies it. And a lot of the work, we were the first to demonstrate that this is actually a viable alternative as a material for external strengthening. Another showcase is ultra high performance concrete, or UHPC, also for design or replacement. It is a high performance material. You can see in the center there, it contains a lot of steel fibers that are embedded in it. So it's a fiber reinforced cementitious material. And it's something that is relatively new in the commercial marketplace. but has seen a lot of use in high performance areas where you need either extremely high strength or you have a low tolerance, so there's a reason why you need more strength in a smaller space. It's interesting because it has compressive strength almost as high as some kinds of steel, and it also has tensile strength, which gives it fairly unique local and global behavior. So a lot of the work that my team has been working on is how to understand the multiple states of stress that exist within the material and the sort of interesting shear type failures that we see develop. So in this particular case, some of the examples here are the interfaces between, for example, fiber reinforced polymers and normal strength concrete as hybrid materials. So a lot of times it's too expensive to use UHPC by itself, so it gets combined. And therefore it becomes another nonlinear interface problem that is a thread through a lot of the work that I do here. Another example is accelerated bridge construction, which is a very broad area, a lot of investment and research in this area. But very particularly, we're moving away from typical cast-in-place construction where everything's done on the job site, and instead people use precast or prefabricated members that are brought from the factory to the job site where they're assembled. And obviously there's economic advantages, not as much downtime, but there's also better quality control, and you can do more things than you would have been able to do on site. The kind of challenge there is that the locations at which you connect them together are also typically the regions that have the largest demands, and therefore there's some challenges for the types of materials and detailing that we use. The example that I'm showing you here is one of several, but we have done some very large-scale testing here at the UCF Structures Lab using what are called grouted sleeves. You can see those on the right-hand side where the bars that extend out of a cast-in-place or a precast footing are connected to a column that you can see, which has the recessed holes, so essentially mating the two parts together. And what we've been able to show here with these is that even in seismic situations where you have extremely large lateral demands on these systems, that we can not only mobilize the same strength and stiffness as you would from a cast-in-place solution, but we're actually also able to control the location of the formation of damage away from what we call the capacity protected members. So we're able to essentially control where things get damaged. And this is something that also leads to all sorts of interesting modeling problems because we develop large amounts of damage and localized nonlinearities at very discrete locations within the members. So we've done a lot of work on one-dimensional, two-dimensional, and three-dimensional modeling for this. And then finally, seismic-resistant design and analysis of bridges. So taking a full-scale reinforced concrete bridge and analyzing it under seismic load. There's a lot of modeling challenges, both from theory, but also to just implementation in software and making sure that users are aware of the choices and the consequences of their actions when they're using this on the design floor. So I've worked on this for many years, both from the context of just modeling and formulation, but also from the probability side. So obviously the earthquakes are sort of a stochastic hazard, and therefore the response that we get is well, not only highly nonlinear, but highly uncertain. And so to make decisions based on not only unknown or uncertain response, but also the consequential damage and losses that may occur is something that's of broader interest in performance-based engineering. So it's something that I've worked a lot on, and extending it all the way to, for example, carbon footprint of repair, or what are the sustainability actions that you can take based on models and their response. So just very briefly, some of the things that I'm working on currently already in the near term, and one of the more recent ones relates to the use of technology for detecting subsurface or non-surface processes, such as some of the nonlinear interfacial behaviors I was mentioning. And then studying disaster resilience under many types of hazards, so including in hurricanes, very pertinent to this area. And then how can you actually make decisions for design that actually are informed through disaster resilience. More studies on modular precast accelerated bridge construction using different types of materials, and then functionally graded and multifunctional materials, but with the eye towards satisfying design requirements or constraints for multi-physics type situations. So, 3D printing physical infrastructure. And then finally, the application of probabilistic tools and uncertainty methods in engineering, mostly through modeling, for prediction of uncertainty in storm surge and the thermomechanical responsive structures to fire. So those are two of the more interesting recent ones. Some of the more specific collaborations and proposals I list at the bottom, which you can read, but these relate to things that I'm already doing with faculty in our college and outside of our college, in College of Science. In the longer term, some of the things that I maybe have done in my career but are looking to return to would be probabilistic life cycle assessment. So this is something that obviously has a strong basis in the work that I've already done. And then how we can incorporate hardware in the loop type simulations where we include uncertainty in the analytical and the experimental components. And then how we can make some decisions at the system level regarding the behavior of multiple pieces of infrastructure in the presence of uncertainty. And then a little bit more specifically related to modular construction, but can we use articulated systems where we actually have things that are free to move, and here for purposes of wind-resistant design. And then finally, you know, is there a place for machine learning in actually discovering or maybe rediscovering fundamental behaviors of structures that are not really apparent from, you know, traditional experimental or numerical techniques. And then I don't want you to believe I'm not interested in teaching. It's something that's very dear to me, and I have some software actually that I've worked on for many years that I've incorporated into my classes, but I've never gone to do any formal curricular development. So that's something that's on the agenda. So I have some specific needs as it relates to wind tunnels as a hardware item, but more if we're moving or making a paradigm shift towards non-cast in place construction, it involves obviously, you know, economy and policy, but, you know, labor, and I think there's a lot of broader aspects to it that would make it interesting to study. And then finally, collaboration, something that's inherent in everything that I have done and what I plan to do. So my skill set is heavily related to solving nonlinear problems and numerical methods. I'm very good at solving problems that aren't necessarily my field, so I'd be more than happy to collaborate with anybody. And then applications of probability and uncertainty. So those are the two areas I feel I could offer if your project has a need. And these are just some recent collaborators in the last year or two, and obviously I'd like to acknowledge the work of my students and my colleagues and the funding agencies here at UCF. So thank you very much.